So from now onwards, we'll discuss. Till now, we have just discussed about the MOSFET device. So my slide is visible, right? You're able to see this slide. Hello.
Yes, sir.
My pointer,
Yes, sir.
yeah, mouse pointer. Also. Okay, great. So now, till now, we have discussed about the MOSFET from device perspective, its operation, its characteristics. So now onwards, we'll go to now the from device to we'll go to the circuit part. So we'll start with inverters. So why do we start with inverter? Because if we have a very good hold on the analysis of the inverter to analyze other logic gates or other logics, it is very easy like that. So the base is basically trying to understand the CMOS inverter. So if we say as normal inverter, like other than CMOS, like if any inverter, so we know that it's a simple, right? It's just inverting. If I have a logic 0, the output will be 1, and if I'm sending 1, it's 0, like that. Now if we go for the ideal characteristics, if I go for the voltage transfer characteristics, so VTC, which is termed as VTC of an ideal inverter, it looks something like this. So whenever my V in is near around 0, less than VDD by 2, the output is high. The output is high, or it's a logic 1. So VDD is termed as logic 1 and ground as logic 0. So and whenever my input is higher than VDD by 2, this is logic 0. So this is the basic definition of an basic definition of an ideal inverter. So here the important definition here is this threshold voltage of an inverter. Note that this threshold of an inverter is different than the threshold of the MOSFET. So we'll try to see, we'll use different notation. So generally VTH is used for the threshold of the inverter, and we'll try to use VT0 for threshold of MOS, right? So we'll try to use VT0 for threshold of MOS. So please don't get confused with the threshold of this inverter. So threshold of inverter is the VDD by 2. So where basically this VDD by 2 is the based on this, that this is I should say the tripping point, or flipping point, like that. So now based on the type of inverter that we design, these characteristics will vary. So this is for an ideal one, but depending upon the type, or we'll see what are the different types of an inverter. So depending upon that, these characteristics may vary. So it may be something like this is an ideal, but in the real case it may be something like something like this. So right, so it may be it will not be a sharp brick wall kind of characteristics, rather there will be like there will be some it will be smooth like that. So and depending upon how how this depending upon how we design an inverter or what kind of topology that we take, these characteristics will vary like that. So now there are different possibilities. So generally the NMOS inverter is defined something like this. So note that I'm using the currently I'll be discussing from this book by Kang and Leblevici. So so I think I have like the full details of their book you can get in the first slide. So you can get the complete details of the book here. So so they have used this. They use this different notation of this NMOS. So for this NMOS, this kind of notation is used. This arrow is inside because the channel that formed is of N type and the substrate is P type. So that's why this kind of arrow is used. So that they are trying to use the convention of this PN junction, right? For PN junction, we use this arrow from P to N, right, in a diode. So similarly, because the channel is N type and the substrate is P type, that's why for this NMOS, right, this kind of this arrow is used like that. So anyways, so this N, I'll have this my NMOS here, so which is the main driver, and the load can be different. So we'll see that there can be different load, like people they have designed different kinds of load. So this load can be different and different types. So, and the input will be applied to the gate of this NMOS. So this is the V in, which is basically the VCS. So this V in control the VCS of this NMOS, and depending upon this load, this VTC curve will vary like that. So we have this kind of we have this kind of inverter where this load is an simple resistance R. So simple resistance is used. So you can say that this is like a common source amplifier, but this also acts as an inverter, because whenever my input is high, or like VDD, so the transistor will be conducting and the good amount of current will flow, and this voltage will drop, and whenever my Bin is 0, this transistor will be in cutoff region and this will go to VDD. So again, we'll come to the complete analysis of this inverter eventually. So here I'm just giving a highlight. So, and this load can also be a again NMOS device. So NMOS device with diode connected load, right? It can be an NMOS device with diode connected load. So again, this also acts an inverter. It can be with a it is not necessary to be diode connected. We can apply some different voltage here, and then it can also, this is also a different kind of inverter, and we can go for this is a native kind of device. So here the threshold voltage is very small. Threshold voltage is very close to 0, right? We have discussed about enhancement and depletion type of transistor in the previous lectures. So where the threshold voltage can be positive or threshold voltage can be 0. So we can also design an inverter with this diode connected load, and the threshold of this inverter threshold of this device can be very small, like that, close to 0. So these are the different kinds of inverters. So finally, this is the ultimate, which most is commonly used, the inverter when this load is a PMOS device. So you can see the arrow is opposite. So in all these cases, the device was NMOS, but here we are going for the CMOS inverter, like where you are using for both PMOS and NMOS device. We are using this PMOS and NMOS device. So it's something kind of we can define it as a switch, right? Depending upon what is the input here. So this is the final CMOS inverter. So again, the input is also again applied to both the gate of the PMOS and gate of the NMOS, like that. So now in this couple of lectures, what we'll try to do is we'll analyze this one of this inverter. We'll not try to analyze all the different kinds of inverters, because I like too much time will be gone if I do this kind of analysis. These analyses are quite similar. So if I do analysis of this inverter, then the analysis of these inverters are quite similar to this. Then finally, we'll after discussing the analyzing this one, we'll directly come to the analysis of the this CMOS inverter, because as I have mentioned earlier, this is most widely used compared to the other type of inverters. Clear, right? Hello, any questions?
Yes, sir.
Okay, so now next let's discuss the some of the characteristics of the inverter that what we want to see. Like as I have mentioned earlier, that the actual characteristics of the inverter will not be an ideal brick wall. Rather, it will be some kind of some kind of like the smoothing, like that. There will be a smooth behavior. There will not be a sharp transition like that. So here we are mainly focusing on the static behavior of the inverters. We are not at this point of time, we are not dealing with the dynamic behavior like that. What happens like depending upon the speed of the signal. So here mostly will be discussing the static behavior of the inverters like that. So this is the VTC, or the voltage transfer characteristics of all the different kinds of inverters. So here we have this five parameter that we are supposed to check to decide whether it's a good inverter or bad inverter, like that. So what are these five parameters? So we have this VOH. VOH is the maximum output voltage when the output level is the logic 1. So whenever it is logic 1, wherever the input is almost close to 0, what is this level of the what is the maximum voltage that it can go, like, so it can be VDD or it may be less than VDD, VOH, like that. VOL is the minimum voltage when the output level is logic 0. So whenever it is logic 0, so what is the what is the minimum output voltage, right? What is the minimum output voltage that it can go? So that is the VOL. So this is the minimum and this is the maximum. Maximum how much it can go to define a logic 1, and VOL is the minimum how it can go to define a logic 0. So this is in terms of the output voltage, output of an inverter. So this is in terms of VOL, and VOH are in terms of the output of an inverter. Now from the input side, VIL is from the input side, right? From the input side is the maximum input voltage, which can be interpreted as 0, right? To maximum, this is VIL is the point, all the Vin which is less than VIL can be interpreted as 0, but after VIL, it's we are not sure, like it's ambiguous like that. So at least till VIL we can say that the input of the input of the inverter is 0. Now how do you define based on this curve, how do you define where is this point VIL? So this VIL is defined at the point where we have this slope, like that, where the slope of this V out V in curve is -1. So where we have this slope dV out by dV in, which is the slope differentiating this voltage with respect to V in. So wherever the slope is -1, I will call that the point or the V in as VIL. Similarly, VIH is defined as the minimum input voltage, which can be interpreted as logic 1. So this is the point. So any value higher than this can be termed as the input to the inverter is logic 1, but below this point again it's ambiguous, like especially when it is in this region, it is like we are not very sure what it is, like that. So and how do we define this VIH point? To calculate this VIH point, again we need to take the derivative of dV out by and dV out with respect to V in, and then equate it to -1, and this is the point where the slope is -1, right? So any value, any input higher than VIH is termed as logic high. And VTH is again the inverter threshold, which we have discussed earlier. So how do we define this point? VTH is the point where V out is equal to V in. So this is the threshold of an inverter where this is the point where my input and output are equal. Like that. Clear? Is it clear? Hello? Any questions till this point? No questions, right?
Excuse me, sir.
Yes.
Sir, VOH is placed in V out and also in V in.
Can you repeat, please?
VOH is placed at VOH, in V out plot, and also V in. There is two value of this one.
Oh, okay. So what it means is, if suppose I have a 2 inverter here, good observation. So suppose the output of this inverter is VOH, right? So suppose the output of this inverter is VOH, suppose it has gone to logic 1, so then of course this will be going down, right? So then we'll define this point as VOL, right? Because we know that the input of this inverter cannot go beyond VOH, right? This is the maximum voltage the input of this inverter can go. That's why we are marking here, right? So the maximum voltage the input of this inverter can go. So at this value, what is my this output of the next stage inverter? So at this point, the output of the next stage inverter will be VOL. Getting right? Able to follow?
Yes, sir.
So just to define this VOL, we are just claiming to going for, okay, if this is the maximum voltage in whenever the input is the maximum voltage situation, what is my lowest output voltage at this output of this inverter?
Okay, sir.
Okay. So now we'll go next. So now again, so we'll come to the concept of noise margin. So these are like various definitions. What I'm trying to do now here is trying to cover before we actually analyze a particular inverter, we are just trying to define the various parameters of an inverter. So what all parameters that we should see that to decide whether this is a good inverter or it's not a very suitable inverter, like that. Now again, there can be a noise like if I am connecting multiple inverters here, so definitely I'll be connecting through the metal lines, right? But there can be some other adjacent metal line, other signal line, right, which is running near to this metal line, and they may be doing some kind of switching activity, right, going from up and down, right? The signal may be going from up and down, and because these high frequency components are there, so there can be coupling of noise, right? There can be a coupling of noise to these inverters, like that, sorry, to this interconnect, so which may be affecting the performance of this chain of inverters. So that's why it's very important to understand in this scenario, to understand the concept of noise margin, like how are we making sure that, okay, even if there is a noise that is coming here, that my beats here are not clipping around, right? Because it can also lead to a fault switching, right? Because if there is a noise and if that noise is very big, so how I'm making sure that the logic level of these inverters are maintained. So that's why it's important to characterize the inverter based on noise margin. So I think just, So now suppose the input to this inverter is VOH again. So then the uh, output of this inverter will be definitely VOL, as we have seen in the previous, as we have discussed in the previous slide. Now the maximum allowable voltage range will be the VIL, right? So as we have known, so suppose if this is the VOL, this is the lowest voltage that is applied here to this inverter. But again, if so this is in the logic 0 state. Now as we have seen that if it is higher than VIL, there will be a problem, right? So as you have seen here, it cannot be higher than VIL. If it is a logic 0, it should be always lower than VIL. So this is the VIL is the maximum allowable voltage, right? So I have applied a VOL here, the lowest voltage, and VIL is the maximum allowable voltage. So if due to the coupling of the noise, this VOL or the voltage here crosses VIL, if VOL plus the noise, if crosses VIL, then there will be a issue. However, if it is even if the noise is coupled, and if the overall VOL plus the noise remains less than VIL, then we are okay like that. So that's why for this lower end we define as VIL minus VOL is my noise margin. So if we can see here, right, so this is from the input region, right, and this is from the output, right. So due to the coupling of the noise, VOL can either even be lower than VOL, because if the noise is in the opposite direction, it can maybe lower than VOL, but generally it will be VOL. But so this is my margin, right? This is the margin. Like when as long as the signal is between this level, if it is lower than that, it's no problem at all. But generally the defined is, this VIL minus VOL will give me the noise margin at the on this lower side. So here we are plotting the VIL and V in, and here we are plotting the V out. So this is how the definition of the noise margin at the lower level comes, like this one. So again I am mentioning, so which is the difference between these VIL and VOL, right? So this VOL is the minimum voltage that can be applied in the inverter, because we have the input as VOH, and VIL is the maximum that is allowed, like that. Now if my input is low here, and of course this is VOH, right, it will go to the if suppose a very low level, this is very small VOL, and we have the output has gone to the highest voltage VOH, right, VOH. But then this, if after coupling the noise is getting coupled in this interconnect, VOH plus the noise can be in a negative voltage, right? Noise can be a negative voltage. So then it should not be less than VIH. If it is less than VIH, again my input to this inverter will be invalid, right? As you have seen here, so it should be in this range. It cannot be lower than this VIH, right? It should be higher. So the difference between VOH and VIH is termed as the noise margin on the higher high value, like that. Noise margin VOH minus VIH. So with this signal at this one to interpret as logic high should not be less than should not be less than VIH. So this difference is defined as noise margin on the logic high, like that. So again here also we can see here the output of the input inverter can be VOH, and So, and this is the input of this stage inverter. So we can see here, this is the difference, like this is the difference, or this difference is termed as the noise margin for the logic input high, like that. So VOH minus VIH. Is the definition clear? Hello, any questions on this? Okay.
No, sir.
If we don't have any questions, we'll proceed next. Now, the term, you see, if we have seen here, we have used a negative slope here, like which is -1. Then one may ask, why we are considering this -1 at a point? Why not the other point here, like -2, -3? Why are you defining this -1? So the reason here is, what happens if you see here, if you see in terms of the gain of this inverter, right, which is basically this dV out by dV in is basically the gain of this inverter, right? Gain of this, I should say this gain. This can also be used as an V out, and V out, change in V out with respect to change in V in is the gain, right? So this, the gain of the inverter here is -1, but if you see here, the slope is more negative at this point, which is higher than 1. So what happens is, if I have some noise, it gets much more amplified in this region. However, if the noise is coupled at this region, whenever it is there, the noise is not amplified much. So that's why this can be set as a boundary, where if it is beyond lesser than this point, the noise gets less amplified. Whether the noise is in this region, the noise gets further amplified. So let me come to this one. So I can define my V out as a function of V in, right? So this is the VTC curve, which of course this is a non-linear function, it's not a linear one. So V out can be defined as a function of the V in. So now in my case, if the noise is added, there will be some noise, there will be noise that will be added to V in, right, as we have seen here. So there is this noise that is getting added to V in. So that's why it will disturb the function of this inverter. So V out is a function of V in, but however now our V out is function of V in plus this delta noise, which is coming from the other circuits, like that. So now if I go for a simple first order Taylor series expansion, I can expand this V out something like this. So V out equal to F V in plus dV out dV in, which is the differentiation of this one into this delta V noise, plus of course there will be higher order terms. Suppose for our approximation we are just neglecting this higher order terms, so we are just considering this this one, like that. So now what we will see, this output is the perturbed output is a sum of nominal output. So this nominal output is the output whenever there was no noise, plus we have the gain of this inverter, and also the noise. So you can see there the final output, the perturbed output is the nominal output, so which was supposed to be this nominal output, into the gain and the external perturbation, like the gain of the inverter and the noise, like that. So that's why it's very important that we focus on the gain of the inverter, or region of the inverter where the gain is very low, where dV out by d in is very small, like that. So if dV out by d in is very small, the noise, the external noise perturbation will not be affecting the operation of the inverter much, like that. So that's why the boundary is taken as where this gain is -1. So whenever the gain is less than -1 unity, then I can say that okay, the noise, whatever the noise that will be getting added to the V in, I can say that the influence of it on the output of the inverter is very small. However, if my gain is more than -1 or less than -1, like if it is -2 or -3, then I can say that the noise effect of the noise on the final output will be much higher. So especially whenever it is in this region, right? Whenever it is in this region, the effect of the noise will be much higher. But wherever it is in this region, when the slope is less than like that, even it's the magnitude of the slope is less than 1, then then less than unity, then the effect of the noise will be much smaller. Is it clear, this point? Any questions on this? Hello, everyone following till here?
No, sir.
Okay.
Yes.
Okay, great. So now next is, okay, so we'll first focus, as we have mentioned, we have seen that, as we have seen that we have this multiple kind of inverters, and depending upon the load that I provide, so we can have different kinds of configurations. So now we'll just focus on, as I mentioned earlier, we'll focus on this inverter with resistive load, and we'll try to define all the all the different 5 parameters for this inverter, and also we'll try to see what are those margins and everything like that. So this is my inverter, where I have this NMOS and I have this resistance R, like that. So let's try to identify different regions of operations. So whenever this input is very small, whenever this input is very small, less than the threshold voltage of this NMOS device, VT0. Not that, again, this is not the threshold voltage of this complete inverter circuit. So whenever the input is less than the threshold voltage of this MOSFET, NMOS device, it is in cutoff region. So then no current will be flowing through these. So ultimately, if no current is flowing through these, right, and then this output will be VDD, right? So no current will be flowing in this region, and this output will be this point will be directly VDD, because there is no voltage drop across this resistor, like that. So this is the situation when Vin is less than VT0, it is in cutoff state. Now, as I slowly increase this Vin, or VGS, right, whenever it is, as soon as it crosses this VT0, it will start conducting, right? It will start conducting, and slowly this output also will be started decreasing from VDD. So it will be started decreasing from VDD. So whenever this my V in is less than V out plus VT0, this comes from the equation of the MOS NMOS saturation region operation. So in that situation, this NMOS device will be in saturation region, and the current through this NMOS or current through this resistor, which are the same, will ID equal to IR, will be defined by simple MOSFET equation. This is the VGS minus VT0 whole square, Kn. So here the note that Kn here is mu n Cox W by L, right? So this is this Kn constant, so we have to remember that. So mu n is the for NMOS, that's why it's written as N. For PMOS it will be mu P, like that. We'll come to this mobility maybe later on, the mobility things. So anyway, so this is the again MOSFET equation, and again here we are considering the effect of lambda as 0. So, and the short channel effect for just to simplify the analysis, just currently we are just considering the lambda to be 0. Lambda is not 0, but we are considering, like, so that we can easily simplify the stuff. We'll see why we are doing it later on, but just for at this point of time, we are to simplify the analysis, we are putting it as 0. And if again, as I am increasing my input voltage, whenever it will cross this V out plus VT0, whenever it will be very high, like higher than the output by VT0, right? We know that the transistor goes to the linear region of operation. Whenever this input will be higher than the output by threshold voltage, we know that this MOSFET will be in linear region, and then I can get my current as, which is again ID through the current through this NMOS, which is also equal to the current through this IR or resistance, and it will be given by this linear region equation of the MOSFET. So I'm continuing. If you have any doubt, if just stop me whenever you want. Like, feel free to stop me like that. So now, if I try to plot the VTC of the inverter, it will look something like this. So this is my VOH, right? VOH, as we have seen, right? Whenever it is in the cutoff state, IR is 0, then Vout is equal to VDD. Vout is equal to VDD. Just 1 minute. So Vout is equal to VDD. So the maximum voltage this inverter can go it can go to the VDD. So that's why, you know, VOH is equal to VDD. So this is how we find the VOH. Now, how do we find the VOL? So suppose my input is highest VOH or VDD or equal to VDD, then what is my voltage at the output node? So this will come to be VOL, like that. So as I have mentioned here, this is how we calculate the VOH. So when Vin is very small, Edmond is cut off. So the maximum output voltage in this situation is VDD. So that's why we have this VOH of this inverter as VDD. Now for the calculation of the VAL, imagine the input is the highest, right? Suppose the input or the previous test inverter has gone to VOH or the highest voltage. So suppose this input here is VDD, then what happens? Whenever this input is VDD, right? So whenever this input is almost in the VDD, you can see here that the output is very small. This output will be very, very small because huge amount of current will be flowing through here, and there will be a huge drop, and because of which, from inspection, we can say that this transistor has gone to linear region, right? At this point, NMOS is in linear region. NMOS is in linear region, right? This NMOS is in linear region. So and then I can write the linear region equation for this MOSFET. Moreover, I'll have another equation. I can write the for this transistor, for this resistor R, right? For this resistor RL, I can write the I can write this expression, right? VDD minus V out by R will be the current flowing through R, right? IR, like that. And the current flowing through this will be the current flowing through the resistor, and the current flowing through the MOSFET will be this linear region equation, right? The ID across the MOSFET will be this Kn by 2 into VDD minus VTO dot VOL. So VOL is basically the VDS. Currently we are considering to find out the VDS, and of course we are trying to calculate which is basically the VOL. Basically the VDS is the VOL, right? V or VDS equal to V out, or now in this situation it is VOL. So VOL square, and now we can equate this to the current across this resistor, which is VDD minus VOL by R, right? Which has come from this equation, like that. So now by solving this, so you can see now we have a quadratic equation in terms of VOL. So if I just simply solve this quadratic equation of the VOL, then I will get the value of VOL. Right? So if I just simply solve this quadratic equation, rearrange this quadratic equation and solve it such that the solution lie between 0 and VDD, right? It cannot go beyond 0 and VDD, because this quadratic equation will have two solutions. So only one of the solution, which is this, basically will lie between 0 and VDD. If it is beyond this range, we can turn that solution as invalid. So, and one of the solution will lie beyond this point. So we'll see that from this we can find out that this is the value of the VOL. So is it clear how the VOL is calculated? Any questions?
Yes, sir.
Okay. So the next that we will see is how do we calculate the VIL. So basically we need to calculate this VIL, right? VIL. So if we see this VIL, we see that the at this point, right, we need to take the derivative. So if we see the region of operation, the output is almost close to VDD. The output is almost very close to VDD. So that's why the NMOS is in saturation region, right? Because it's the output is higher than the V in. So from inspection we can say that the NMOS is in saturation region. So what I can do is I can write again the current equation for this resistance and the saturation region, saturation region equation for this NMOS, right, for the calculation of VIL. Similarly, if called the calculation of VIH, you can see that the NMOS is again in linear region. NMOS is in linear region. So I can write down the current equation of the MOSFET in linear region, and again the current equation of the resistor is fixed. Resistor RL is fixed. So I can write down and I can equate it and do the differentiation, and I will get VIH. So here in this region, NMOS is in NMOS is in saturation region. So I can just so to calculate the VIL, as I mentioned, the NMOS is in saturation region. So I can equate the current through this resistance, which is this one. So basically I am trying to equate IR, and this is the current through the MOSFET. So because IR equal to ID, and because the MOSFET is in because the MOSFET is in saturation region, so because the V out is much higher than V in minus VT naught, satisfying the saturation region operation of the MOS. So if I just equate it and then I can differentiate it, because I need to get dV out by dV in and equate the slope to be -1 to get the VIL. So now if I just differentiate this equation with respect to VIN, right, VIN, so I can just do a simple differentiation and then substitute this dV out by dV in with -1, and my this input will be I can replace it as this V in as VIL, because I'm now from input perspective I'm trying to find out the I'm trying to VIL. So substitute this dV out by dV in with -1 and V in with VIL. So and from this we'll get VIL. So VIL is equal to VT0 plus 1 by Kn into RL like that. So this is the expression of my VIL. And of course, if I just substitute this VIL in this previous equation, then I can find out even the output voltage whenever my input is VIL. So using this simple expression, I can find out what is my output voltage when my input is VIL. Again, to find out the VIH, again we'll follow the same step. We'll write the current equation for this resistance, which is VDD minus VDS by RL, and then we'll try to equate with the current equation of the NMOS. So as I have mentioned, in this region the MOS is in linear region, because if you see here the input is very high, whereas the output has become very low. So based on the inspection, we can say that this MOS is in linear region. So I need to write the linear region equation for this one. So if I write the linear region equation for my this MOSFET, which is ID basically, and again I'm equating IR, the current through this resistance, right? So then now if I just equate these two, and again if I differentiate this V out with V in, I'll get this kind of equation, right? Differentiating the V out with V in, and now again using the same procedure, substitute dV out by dV in with -1, and now now in this situation V out will be V in will be VIH, so this V in will be VIH, because basically we are trying to V out will remain the same, V in will be VIH, because we are trying to calculate the VIH here. So substituting dV out by dV in with -1 and V in with VIH, what we get is we get this expression, simple expression. So again, what we get an equation here is we get an equation which has two unknown variables, VIH and V out. We still don't know what is V out, and we want to find out VIH. Now if we see here, we have two equations here with two unknowns. So here also we can see here, if I replace this V in with VIH, I have an equation here which has two unknowns of VIH and V out, and here also I have an equation number 2 which has two unknowns of VIH and V out. So using simple like if we solve this 1 and 2 by substituting this 2 in 1, then by substituting 2 in 1 we can get this kind of expression, which is a quadratic equation, which is a quadratic in terms of V out. Now if I just solve this equation and get a positive solution, right? So this quadratic has negative solution and a positive solution. So the positive solution of this, because the VIH will definitely be a positive number, so the if I do this solve this quadratic equations, I'll get this V out, which is when V in equal to VIH, right? I will get this expression, and if I just substitute this value of V out here in my equation number 2, then I will get the expression of the VIH here. Okay. So this is the expression of by VIH. So till now we have until now we have covered VIH, VIL, VOH, and VOL, right? So like that. So now, of course, there is one more, which is the threshold voltage of the inverter. So to find out the threshold voltage of the inverter, so which is at this one. So I'm leaving it as an exercise for you. You can just try to do it yourself. So at this region, NMOS is again in saturation region. NMOS happens to be in saturation region because whenever V in equal to V out, right? So VGS and VDS of this MOS is in equal, so definitely the NMOS is in saturation region. NMOS is in saturation region. So again, using similar kind of analysis, trying to equate this current and the NMOS current, we can very easily, because already B in and B out are like that. So we can very easily find out VTH. So this is the point. So at this point we have VTH like that. Okay. So now if we try to plot the VTC of the resistive load inverter, what we'll see that we'll get this kind of plot. We'll get this kind of plot for different values of KNRL. So if you see here, in most of the expression of VIH, or if we go to the VIL, this KNRL has come into picture multiple times, right? So that's why depending upon this KNRL again, this Kn is mu n Cox WL. So of course the designer doesn't have control on mu n Cox. This is based on the process. So at least the designer has an access to W and L, and of course the resistance, of course this resistance RL, right? So if I vary WL and resistance RL, you will see that we'll have different kinds of characteristics. So you can see that if my KNRL is very small, my VOL has VOL is at this point, which is very large, right? Whereas if my KNRL is very higher, then I can get a VOL smaller like that. So similarly, VTH is also getting affected because of this KNRL. Okay. So I wanted to show some simulation on this. Next day we'll see like how we can do this characterization and see yourself by doing simple simulation. So of course all of you don't have access to cadence now, and that's why I just wanted to show like how simply we can do this simple analysis even in some SPICE solver. So next day we'll discuss that. So if you have access to cadence, you can do this, but I think only few has the access to cadence. But even you can do this kind of analysis in simple SPICE, like at least SPICE. So I wanted to cover this one today, but somehow now the time is already 11 o'clock. So and that's why we'll stop the discussion here, and we'll cover how we can do this analysis in even in LT SPICE and all like that. Then we can try to see how, with parameters, change in parameters, how it all happens, and also we'll discuss why why this kind of behavior, this kind of the curve sees because of increase in CAN RL. What's the reason? So we'll try to discuss in the next class like that.